Hello and welcome to lecture 2 of the theory of computation course. Right, so in the lecture 1 we gave a brief overview of the course, and we ended by saying asking you to read chapter 0 from Substrings, which gives some basics from discrete math such as sets, functions, relations, logic, theorem proofs, etc. In this lecture we will actually see some basic information that will help us understand that will help us set up the notation and understand the rest of the course. Right. So the first thing I want to say is that we will usually deal with computational questions. Right. So it will be something like so simple computations, things like if you add like 25 and 62, what is the sum? Or if you multiply 25 and 62, what is the sum? What is the square root of 400? What is the cube root of 400? Right. So these are all computational questions. Right. These kind of questions also occur in day-to-day life. Right. So how in our course we will try to represent all of this as a string input. Right. So in all these questions there is an input, and then we will try to convert, or we'll for most of the lecture, or for most of the course, we'll try to view them as a decision problem. Right. So we'll try to focus on questions of the following type, meaning does this number have a certain property? Right. So for instance, one question could be, is the number 400 a perfect square? So the answer is yes, because 400 is the square of 20. Is the number 500 a perfect square? The answer is no, because 500 is not a perfect square. There is no integer which you square you will get 500. Right. So we will, for most of the course, we will consider problems like this. These are questions of this type, where the answer is a yes or no answer. So these will be called decision problems, because it's a yes or no answer. The answer is not like asking to add two numbers, so the answer is something else. Right. So the answer is another number, so there is an output. Right. So we will mostly focus on decision questions. So the decision questions can be represented like this. Right. So for instance, one question is this number even? Right. So I could write it in the following way. Right. I could write it, I could give a set like this. Right. And ask, is the given number in the following set? Right. Maybe I'll use a darker, slightly different color. Is a given number in the following set? So which means if it's a positive integer, it's like, is it in 2, 4, 6, 8, 10, etc. So it's like the same question in another form. Or if it is binary integer, then it's like asking, is the given integer in 1 0 1 0 0 1 1 0. So these are like 2, 4, 6, 8 in binary, right, etc. So is the given number in this set? Right. So this is the question that we have. So the point I want to mention here is that, so you have an input which is a number, and you have a set which is a collection of numbers, and you are asking whether the input belongs to the collection. Right. So this is another way to model the decision problems. So is this number a perfect square? So you can give a list of all the perfect squares. This will be an infinite list, but you can ask, does this number belong to this list? Right. Another question is the given binary number, right? So it's a binary number is given, is it a palindrome? So palindromes are those numbers, or are those strings that read the same from left to right and right to left. So for instance, the word radar is a palindrome. RADAR reads the same from left to right as well as right to left. Right. Another word, the word noon is a palindrome, NOON. So if you read it from left to right or right to left, it is the same. So you can even make palindromic sentences, but let me not get into that. So the question is whether a given binary number or a binary string, is it a palindrome? So another way of asking is a given number in the following set, which is a set of all palindromes. Right. So 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, etc. Right. So is a given number, does it belong to the following set? Right. and is a given number a perfect square, right? So in other words, it is a given number in, let's say, let's say the given number is only positive, right? So 1 is 1, the next perfect square is 4, which is like 1 0 0 in binary. The next perfect square is 9, which is 1 0 0 1 in binary. The next is 16, which is 1 followed by 5 zeros. The next is 25. So 25 is 16 plus 8, 24. There is no 4, there is no 2, there is 1, right? So this is 25 and so on, right? So it's a given number in this sequence is what we are asking, right? So I'm just giving different examples of questions that we will kind of look at during this course. Another question could be, since we have all been dealing with numbers so far, another question could be, does the given English word contain the letter A, right? So or in other words, is the word in the following list, where the list is set of all words with the letter A. So A, and, at, I don't know, then other words like bat, cat, and so on. So you could fill it up with many words. So this is just some one letter word, and some 2 letter words, and some 3 letter words, and so on. But is a given word is in this set, right? So the point I am making here is that all of the problems, or most of the problems that we will consider in this course, will be of this type, which will not be of the type like given these numbers you compute this, right? That kind of thing. It will mostly be of this type. It will be of decision problems. So you have an input which is comprising of some strings, some number, or some word or whatever, and you have a set, and you want to see whether this input belongs to this set, right? So the first 3 questions here, we used the input as well as the sets were of binary, right? Meaning the numbers in the sets were binary. In the last question, the input was a word, English word, and the set is also consisting of English words, right? So now, why I'm saying this is that this will help us set up some basics that we will use throughout the course. So the binary used zeros and ones, and the English word used words used English symbols. So these things are called alphabets, right? So binary, the alphabet is just 2 digits or 2 bits, 0 and 1, and the English, the alphabet is all the 26 letters, 26 English letters, right? So this will help us set up some basic terminology that we will use throughout the course, right? So we will deal with strings. Strings are just a bunch of symbols. So these are all like a bunch of numbers, like, or 0 1 0 0 or 0 1 0 0 0 or 1 1 0 0 1. All of these are strings, right? Over the respective alphabet. Okay, so like bat is a string, B-A-T. It contains 3 symbols, B followed by A followed by T. So strings contain symbols from a certain alphabet, and another way to say the same thing is that a string is over an alphabet. So we say that string is over an alphabet means a string contains symbols from a certain alphabet. So what are some standard alphabets that we will consider? So one is binary alphabet, which contains 0 and 1. Another one is decimal alphabet, which contains all the 10 digits, 1 2 3 4 up to 9. Then we have the English alphabet, which contains all the English letters, A, B, C, D, and so on up to X, Y, Z, right? Or you could have any alphabet, right? You could just have some alphabet defined like this, which contains some letters, 3 letters A, B, C, and 2 to numbers 1 and 2, right? So this alphabet sigma 4 contains only 5 symbols. Binary alphabets contain only 2 symbols. So the members of the alphabets are called symbols, right? So binary alphabet contains 2 symbols. Decimal alphabet contains 10 symbols. English alphabet contains 26 symbols, right? And sigma 4. So, and usually we denote the alphabet by using this sigma notation. So sigma 4 contains 5 symbols, right? And strings use symbols from these alphabet. So any binary string is just repeatedly we use zeros and ones, right? Any English word uses letters from the English alphabet. Okay. So a string over an alphabet, this is formally define the same thing. Over an alphabet is a sequence of symbols written one after the other, right? So this is a definition of a string. It's a sequence of symbols. It's a finite sequence of symbols written one after the other. Just some more examples. So 101101 is a binary string. Maybe I'll just use it in smaller case. The word consider is an English string, and maybe 83262 is a decimal string, right? So these are just, which means it's a string comprising of symbols from the respective alphabet. So the first one comprises of symbols from the binary alphabet. This has symbols from the English, and this has symbols from the decimal alphabet, right? One thing that this is small observation is that the first one, the 101101 is also a string from the decimal alphabet, right? Because it contains the symbols that are also present in the decimal alphabet, right? So given a string, the length of the string is denoted by, so let's say sometimes we denote strings by a single like a symbol like W, right? So the length of the string is denoted by a W with these 2 bars around it. So an example 110110, the length is 6 because it contains 6 symbols. The word hello over the English alphabet, the length is HELLO, it's 5. The string 253 over the decimal alphabet, the length is of course 3. So let me ask a question. So consider the word, or consider the string hello there, okay? Hello followed by a space, and then followed by there, followed by an exclamation mark. Is this string over the English alphabet? Again, reminding you, the English alphabet is the set of all the 26 letters A, B, C, D, and so on up to X, Y, Z. So the question is this string hello there, is it a string over the English alphabet? Okay, and the answer is no, because there are 2 things that are not part of the English alphabet. So one is, so it's 2 things that are not part of the alphabet. So one is the space. Space after this hello and there, the space. Space after hello, and 2 is the exclamation mark. So even the exclamation mark is not part of the alphabet, right? So this string is not part of the alphabet given here, but we can make it part of the, or so this string, we can consider it to be part of an alphabet where we had all of this along with space and exclamation mark. So if there is a bigger alphabet with space and exclamation mark as part of that alphabet, then this can be considered as a string that is over that alphabet, but not over this alphabet alone. Okay. So we can expand the alphabet to make this string over that alphabet. Okay. Now let me get into some definitions which will be useful. Of course, we will remind them when some of them need to be used again, but still it will be good to go over them once. So one is W, where W is a string. Superscript R denotes the reverse of the string R, right? So for instance, if W is the word top, T-O-P, then W superscript R is the reverse, which is like T-O-P reverse is P-O-T, right? Another notation is epsilon, written like this. So it's like a 3, the mirror image of this, the digit 3. This denotes the empty string. Okay, so mirror image of 3, this denotes the empty string. And one convention is that what is the length of the empty string? So any string contains a certain length or has a certain length, right? The word hello has length 5, the word empty has length 5, the word string has length 6. So what is the length of the empty string? The empty string has no letters or no symbols. So the empty string by convention is said to have length 0. Okay. Then some more definitions. One is concatenation. Concatenation is where we append one string after the other. So if x and y are two strings, the concatenation of x followed by y is obtained by merely appending y after x. So xy denotes the concatenation, so it is just written xy. So if x is the word top and y is the word hat, the concatenation of xy is written just by xy, denoted xy, is the string top hat without a space. Okay, so I hope this doesn't look like a space. It's just one word, 6 symbols, T-O-P-H-A-T. xy is the string top hat. And just to give an illustration, the concatenation of xr, or the reverse of x followed by y, is a string pot hat, because xr is pot followed by hat. Another notation is the usage x to the power k, x superscript k. This is just x repeated k times, or x concatenated with itself k times. So if x is the word top, x to the power 3 or x cubed, as you may read it for numbers, is merely x repeated 3 times the word top, 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 right? So the x to the power k is the word x repeated k times. So k could be, so where, or for k has to be an integer, right? And what is just one more interesting point. So x to the power 0, which means x repeated 0 times, is actually the empty string. Anyway, this won't be used that much, but I'm just saying. Next is the Kleene star. So the Kleene star of a string x, it's also denoted by x superscript star, is defined as the set of all x power k, right? Where the set of all x power k for all the possible k. So for instance, if x is 10, then x star would be the empty string 10 and so on. So this contains x power 0, x power 1, x power 2, x power 3 and so on. Right. This is denoted, or this is said to be the Kleene star of a string x. Right. So these are all important definitions that we will use. And we even define the star notation, the Kleene star, for over a set of symbols. Okay, so where if sigma is a set of symbols, or sigma is the alphabet, sigma star is the set of all strings using symbols from sigma. So for instance, if sigma is the binary alphabet, sigma star contains the set of all possible strings using 0 and 1. So you first have the empty string, then you have the 2 strings of length 1, then you have the 4 strings of length 2, and then you have strings of length 3 and so on. Right. So anyway, it's a set, it's a collection, there is no ordering. I'm just written down like this just for easiness of understanding. Right. So sigma star is the collection of all the strings which can be created using symbols from sigma. And finally, or not finally, but the definition substring. So V is said to be a substring of another string W. Okay, when do we say V is a substring of W? If there exists strings x and y such that W can be written as x, v, y. So maybe it's simpler to explain it using an example. So maybe let's say the word get is a substring of the word, let's say together, right? Because it's TO and then followed by get and then HER. So the word get happens to appear in the word together, like together, right? So the word get appears as it is in the word together. And maybe another example is, let's say, the string 1100 is a substring of, let's say, 101011100. So here the substring appears at the very end, right? So in this case the y is an empty string, right? So the y is an empty string, there is only x, so this is also a substring. So any string, so V appears as part of the string W, that is when we call V is a substring of W. The last definition, which is also an important one, which is that of a language. Let me just revise the rest of the definitions before we go to the language. So we have an alphabet which contains symbols 0, 1, like the binary, decimal, English are examples of alphabet. String are small sequence of symbols from the alphabet, right? So a string is a collection of symbols obtained from an alphabet. That we define string, and then the reverse of the string W superscript R, the empty string which has 0 length. Concatenation is when you append one string with other. So the concatenation of xy, the concatenation xy is not the same as the or need not be the same as concatenation yx if the strings x and y are different. X power k is x concatenated with itself k times. Kleene star of x is set of all x power k, right? For k greater than or equal to 0, and for a set of symbols sigma, right? Sigma star is a set of all strings that can be generated using symbols from sigma. Substring, V is a substring of W if V is like the part of W. By that we mean that we can add something to the beginning of V and end of V to get the string W. So, two examples to clarify. Finally, we come to a language. So, a language is just a collection of strings over sigma. So, it is just a subset of all the possible strings. So, sigma star we defined here is the set of all possible strings over sigma, right? And a language is just a subset of them. So, for example, any subset of them is a language. So, set of all binary strings with an odd number of ones is a language over 0 1. So, a set of all binary strings with an odd number of ones is a language, because it's a, so you have all the binary strings, right, and this is a subset of them, right. So, you have set of all binary strings which is sigma star or which is 0 1 star, and this set of all binary strings with an odd number of ones is a subset of them. So, that is a language. Another one is the set of, so you have the English alphabet containing the letters A, B, C up to Z. These are 26 letters in the 26 symbols in the alphabet. Now, you can make all kinds of strings using these, right. So, sigma star in this case is a set of all possible strings. Now, if you focus on the set of dictionary words, the words that are listed in a standard dictionary, this is a subset of them, right. So, now the set of all dictionary words is a language over the English alphabet. So, if you know the game Scrabble, sometimes you end up checking whether your opponent lays out some word and you are not sure if it's an actual word. So, then you want to check whether it is there in the dictionary, right. So, you are asking whether the played word is a dictionary word. So, the significance of this, before going to significance, we can even consider this sigma star itself is a language. So, this need not be a strict subset or a proper subset, right. Sigma star is also a language, because sigma star is itself a subset of sigma star. Sigma star is also a language. The empty set is also a language, right. Empty set, or sometimes denoted like this, is a language. So the language that contains nothing and the language that contains everything, these are both the set that contains nothing and set contains everything, these are both languages, and everything in between are also languages, right. So the significance of this language is that in the beginning of today's lecture, we said that we will be mostly interested in decision problems of this type. Is the given number or the given string, does it belong to this collection, or does it have a certain property? So what we have here is that the set, this set over here, let's say the given number is even. So the first set 1 0 1 0 0 1 1 0 etc. So this is a language. So we are asking whether the given string is part of a specific language, and the same thing applies for all the remaining problems, right, for all the remaining questions. So you can consider language of all the palindromes, all the strings that are palindromes, and then you are asking whether the given string is part of that language. So we will, in our course, we will frequently be referring to the word language. So the word language is just a subset of some strings. So instead of asking whether the given string has a certain property, we will consider the set of all strings that have the property and define that as a language, and then we will ask, does the given string belong to this language, right. So that's why the word language is of importance here, the word language or the notion of language. So it is a set of all the it is a subset of all the strings, or it is a subset of sigma star. So giving two examples here, but then you could think of various examples, right. So there are so many examples, that there are so many subsets. Sigma star itself is of infinite size, so sigma star has many possible subsets. Not all of them will have such nice short descriptions in English like this. So finally, I just wanted to say one more thing. We can describe languages in many ways. So one is a brute force listing. You could just list down all the members of the language. So for instance, here I have A followed by AB, followed by ABB, followed by ABBB, and so on. You could just list down the members in brute force. We could have other clever ways of writing, like AB star denotes the same language, because B star contains empty string, then B, then BB, then BBB, and so on. So if you append or you add A before that, you get the strings in the language A, then AB, then ABB, and so on, right? So this is another way to denote the same language. You could also use other set theoretic descriptions, like you could use operations like this, union, intersection, etc. Right? So for instance, you could have, for example, AB star union A star B. This is the language. So this is not the same language, but then I'm using union to take the set theoretic union of two languages. Right? I could even have complement, intersection, and so on. So we can use all this to denote languages, right? So I think that is all that I have in lecture 2, where these are some basics that will help in understanding the remaining content, right? So we saw strings, we saw alphabet, we saw some basics like reverse, empty string, length of the string, concatenation, Kleene star, and so on. Right? What's a substring, what's a language, etc. And from the next lecture onwards, we will be using these notions kind of regularly, and we will start with some simple models of computation. We'll start with what are called finite automata or deterministic finite automata in the next lecture.